Looks terrible, doesn't it? But the driver walked away because of the law of conservation of energy. The law of conservation of energy says that energy can't be created or destroyed. It just changes form. As a race car goes faster, it gains energy. In a crash, the car stops, so its energy of motion must go somewhere. The pieces of the car that break away absorb most of the energy. This protects the driver from serious injury. So when you see a car break apart in a crash, that's good. The law of conservation of energy protects the driver. And that's physics. Watch how fast Indy race cars turn. Cars turn when a force pulls them toward the center of the turn. This force is called centripetal force. The faster a car goes, the more centripetal force it takes to turn. In order to turn at speeds of 200 plus miles per hour, the driver must take advantage of the car's weight. On a bank track like the Indianapolis Motor Speedway, part of the car's weight pulls it toward the center of the turn. The car's weight on the bank track provides the extra centripetal force that lets the car turn at 200 plus miles per hour. And speed, after all, is the point of racing, and that's physics. Look how fast these Indy cars accelerate onto the track. As you watch Indy cars accelerate onto the track, you're seeing an example of Newton's third law. As the car's tires roll forward, they push against the track in one direction. The track in turn pushes back against the tires with an equal force and in the opposite direction. So for every action of the tires pushing against the track, there is an equal and opposite reaction of the track pushing back. In order to make the best use of Newton's third law, the force of the tires pushing against the track needs to be as large as possible. Look how much more surface area this racing tire has. Racing tires are wide and sticky to create more friction and push harder against the track. Newton's third law says that the track will push back just as hard, using that extra force to accelerate the car to the speeds racing fans love. And that's physics. Listen to this sound. Did you notice that change in pitch? Listen again. That change in pitch is an example of the Doppler effect. The sound of a race car coming toward you has a higher pitch, and the sound of a car going away has a lower pitch. That's because sound is a pressure wave traveling in air. The number of waves that strike the ear every second determines the pitch. The more waves, the higher the pitch. Sound waves from a car coming toward you are closer together, and sound waves from a car going away from you are farther apart. And that is the Doppler effect. The Doppler effect causes the sound racing fans love. And that's physics. Indy cars travel down the track at over 200 miles per hour. That's faster than the speed small aircraft reach before taking off. Ground effects of Indy race cars and lift on airplanes come from the Bernoulli effect. The pressure of fast-moving air is less than the pressure of slow-moving air. Airplane wings are designed to make air move faster over the top of the wing and let the slow-moving air under the wing lift the plane. Ground effects for Indy cars are the opposite of lift in airplanes. These special body panels are designed to channel the fast-moving air under the car and let the slow-moving air above push the car to the track. Without the Bernoulli effect, a car going 200+ miles per hour would fly off the track. The Bernoulli effect helps hold cars to the track at high speeds, and that's physics.